How do Neurotech devices listen to the brain's neural signals? Imagine trying to eavesdrop on a busy conversation happening inside someone's mind. That's essentially what neurotechnology devices do when they listen to the brain's signals. The brain communicates through tiny electrical impulses generated by neurons, the nerve cells that make up our nervous system. These impulses are called action potentials or spikes. Along with these quick signals, there are slower fluctuations called local field potentials, which reflected the activity of groups of neurons working together. Neurotech devices pick up these signals and turn them into data that computers can analyze. There are two main ways these devices capture neural signals. The first is non-invasive, meaning they don't need to penetrate the skin or skull. The most common method here is electroencephalography, or ECoG. ECoG uses small electrodes attached to the scalp to detect the electrical activity of large groups of neurons in the brain's outer layer. It's safe, quick to set up, and widely used, but it has lower spatial resolution, meaning it can't pinpoint exact locations very precisely. Other non-invasive methods include functional magnetic resonance imaging, or fMRI, which measures blood flow changes in the brain, and functional near-infrared spectroscopy, or fNIRS, which also tracks blood flow but with light. These methods are indirect but useful for understanding overall brain activity. The second approach is invasive, which involves placing electrodes directly into or onto the brain tissue. This method provides much higher detail and resolution. For example, intracortical microelectrode arrays, often called microelectrode probes, are thin, flexible wires that are inserted into the brain's cortex to record individual neuron activity. Devices like the Utah array or Michigan probes can pick up signals from single neurons, giving very precise information. Electrocorticography, or ECoG, places electrodes on the brain's surface beneath the skull. It offers better resolution than ECoG but is less invasive than microelectrode arrays. These implanted devices can decode complex brain functions like movement intentions, speech, or even emotional states. Modern Neurotech devices use advanced materials that are flexible and compatible with brain tissue. This reduces tissue damage and helps keep the signals stable over time. Some newer technologies are wireless, using ultrasound power or tiny microneedle arrays that sit between hair follicles, making the process less invasive and more comfortable. Once the signals are captured, they are amplified and converted into digital form. Machine learning algorithms then analyze the patterns to interpret what the brain is trying to communicate. This process allows for applications like controlling robotic limbs, helping people with paralysis communicate, or monitoring mental states such as focus or awareness. In essence, neurotechnology devices listen to the brain by detecting the electrical activity neurons produce. They do this either through sensors on the scalp or by implanting tiny electrodes directly into the brain tissue. The choice depends on what kind of signals are needed and how precise the information must be. These signals are then processed and decoded to create a bridge between the brain and external devices, forming the foundation of brain-computer interfaces and many other neurotech applications.